So with that, we will start off with this workshop with the first session of the day, which is the top papers Kaleidoscope. Next slide. So this is the first time that we have this session. So this calls for some kind of explanation. What is this and why? As we all know, the quality and quantity of papers from India in data science has been improving steadily over the years. There are 5 papers in the currently ongoing CKDD conference, 14 in AAAI, 15 in ICML, 7 in NeurIPS, 8 in ACL, and so on. So while the authors present their papers at these conferences, only the conference attendees get to hear them. So we wanted to have a single session that provides a flavor of the diversity and quality of these papers presented by the authors themselves. So this year, we picked 10 papers from different core A-star data science conferences. We tried to make this small sample representative in terms of the conferences, topics, as well as institutions and collaborations involved. And now we present this year's Kaleidoscope, where we will see back-to-back brief 3-minute pre-recorded presentations of these 10 papers. So get ready for a breathless 30-minute trip through fascinating ideas. Raj, I'll share my screen. Okay, just making sure you can see my screen.
Hello, I'm Divyanshu Mandora, and I'm presenting the research paper.
The video is audible as well, right?
Yes, Indrajit.
Okay.
Explanations for Common Sense QA, New Dataset and Models. Our paper has been accepted in ACL 2021 conference, and this is a joint work between IIT Delhi and IBM Research AI India. Common Sense question answering. If we ask a question like, if you are hungry, what will you do? Eat food or play to a kid? Then he would give the answer as eat food. And if we ask the same question to an AI-based machine, our latest word-based machine, 83% of the time it would give the correct answer as eat food. But if we come to the domain of reasoning and ask the question, why to eat food and why not to go for play, then the kid might think for some time and then come up with an explanation like, when we are hungry, our body needs energy. Eating food gives us energy while playing drains out our energy. That's why eating food is the correct answer. But if we ask the same question to an AI-based machine, it won't be able to give such a reasoning. So our work lies to bridge this research gap. So our contributions are multifold. First, to define what does an explanation mean. Then we curate a dataset on top of the Common Sense QA dataset given by Talman et al. In 2019. And then we give models for both, baseline models for retrieval and explanation generation. So an explanation must be comprehensive, refutation complete, minimal, and coherent. Coming to the dataset, we have a question and 4 incorrect choices and a correct choice for every question. So our explanation dataset consists of positive properties to support the correct choice, negative properties to refute the incorrect choices, and a free flow explanation for the whole question. There are a total of 10,962 questions annotated with an average of 2 positive properties per question and 4.3 negative properties per question. Coming to the models, we have models for both retrieval as well as generation setting. For retrieval, we have gold corpus in which the test set properties are present during inference, silver corpus in which those test set properties are absent, but we have another corpus, open mind common sense corpus. For generation, we have a property generation model, XGP, and a free flow explanation generation model. So this is the deep property ranker for the retrieval setting, in which we have BERT-based sentence embedders for question answer encoding and property encoding. For the property generation setting, we have a pre-trained GPT-2 model, which we further fine-tune over ECQA train set properties and OMCS corpus, and further fine-tune over train set queries with proper BOS and EOS, beginning of sequence and end of sequence tokens, and beginning of property and end of property tokens. Here are some numbers in which retrieval over gold corpus, we beat the baseline BM25 by a margin of 100%, and they are the numbers for retrieval on silver corpus and our generation XGP model as well. We also have a free flow explanation generation model. Details can be looked out in our paper. So our data and code links are also available in the paper. Yeah, thank you.
Hello, I am Yash Chandani, and today I'll be presenting our paper exploiting language relatedness for low web resource language model adaptation and Indic languages study, which was accepted at ACL IGC NLP 2021. I'd also like to thank my fellow authors Sarvesh, Vaidehi, Abhijit, and Professor Sunita from IIT Bombay, and Professor Partha, who is at Google Research India. So an overview of multilingual models is that they are a powerful tool in the current NLP domain because of their capability of handling inputs from different languages. But training such multilingual models requires an abundance of resources for all languages, which is a challenge for languages with low web resources. And the relatedness among languages, so let's take a look at Indo-Aryan language family with Hindi as the language with most web resources. We exploit relatedness across two dimensions, script and sentence structure. Like belonging to the same Brahmic script family, there is significant overlap of words between these languages, and languages of this family exhibit common syntactic properties such as subject, object, verb, order. So how do we exploit such relatedness? We suggest these methods: transliteration, pseudo translation, and alignment laws. So our contribution is RelateLM, which is a language model which exploits relatedness between a low web resource language and a related prominent language to incorporate the LRL in an already pre-trained language model using monolingual data and the bilingual lexicons. Using these three methods: transliteration, pseudo translation, and alignment laws. So how do we do this? Given all the resources that we have, we first transliterate them into the script of RPL, and then using the monolingual data and the corresponding bilingual lexicons, we generate pseudo translation, which are just word by word replacements using the bilingual lexicons. And then we first perform MLM pre-training using the LRL monolingual data, and then using the monolingual data and the corresponding bilingual lexicons, we perform alignment laws, which is just MSE laws to bring the contextual embeddings of the corresponding words together. And we experiment with both Hindi and English as the prominent language to demonstrate the impact of relatedness, and in two different settings: bilingual setting where we adapt LRL to a monolingual model which is trained on a prominent language, and multilingual setting where we adapt LRL to a multilingual model which already has one of the prominent languages. And we compare three types of model: eBERT, which is simple extension of a already pre-trained language model using MLM pre-training on LRL monolingual data in its native script. RelateLM minus pseudo translation is basically our method except the alignment laws and RelateLM. And we use Wikipedia for monolingual data set and Wiktionary and CFILT for the bilingual lexicons. We simulate low resource language by selecting only 20,000 documents from Wikipedia. We perform zero-shot evaluation by fine-tuning on prominent language data and then evaluating on test LRL data on NER, POS, and text classification. And we find that in bilingual language models, RelateLM performs best, which shows the power of exploiting language relatedness. And even in multilingual language models where we adapt mWord to ODI and Assamese, RelateLM performs the best here as well. And even RelateLM performs better than eBERT, which is trained on 80,000 documents, which is 4 times more monolingual data, which suggests that efficiently exploiting relatedness is more important than just blindly adding more monolingual data. Thank you.
Hello, this paper is about a network expansion based approach for lifelong or continual learning. And we do this by learning to calibrate convolutional neural networks. My name is Piyush, I'm from IIT Kanpur, and this is joint work with my students Pravendra, Vinay and Prateek, and Lawrence Karin. This paper appeared at NeurIPS 2020. It is well known that lifelong or continual learning methods can suffer from catastrophic forgetting, which means that they typically tend to forget the knowledge acquired from previous tasks when they are learning a new task. Now, an effective way to address this issue is by allowing the network to grow in size, as this figure shows. However, as the number of tasks become very large, the expansion-based approaches can also grow excessively large in size, which may not be very ideal if we wish to deploy these kind of models in resource-constrained settings. In this work, we present an efficient solution for this problem by learning task-specific layer-wise calibrations for the channel outputs of a CNN. This approach results in minimal forgetting while also being highly parameter efficient, as these two plots show. So we suffer from very minimal forgetting as the number of tasks increase, and at the same time, the model size growth is reasonably small. As mentioned earlier, for each task tree, the basic idea is to learn task-specific calibration modules, denoted by CM in this figure and shown in green color. These modules transform the conv layer outputs of a base CNN, which is shown in green or orange color, and make specific. These task-specific CEMs require very few parameters, and that is how we design them. And as an example of the benefits given by this approach, with just about 0.5% additional parameter over the base network, our approach can significantly outperform SOTA on ImageNet 100. Our architecture consists of a base network whose conv layer outputs are shown in orange in this figure. It also consists of task adaptive calibration modules, which are shown as these by these green rectangles after every conv layer output. And we also have a task-specific classification module. Each calibration module contains two sub-modules, spatial calibration module SCM and channel-wise calibration module CCM. SCM contains one parameter per point in the input activation map, and CCM contains one parameter per channel. The base network as well as the calibration modules are trainable. The base network is trained only for the first task, and after that we freeze it. After this, we only learn the task-specific calibration modules for each new task. On Sifartin with 10 tasks having 10 classes per task, as this figure shows, our approach CCLL gives impressive accuracies, shows almost negligible forgetting, while also having negligible growth in the model size as the number of tasks increase. For more results, please refer to the paper. Thanks.
Hello everyone, I'll be talking about least squares regression with Markovian data, fundamental limits and algorithms. This work appeared in NeurIPS 2020. Modern machine learning, especially reinforcement learning, considers data with temporal dependencies, and it is very important part to model the problem at hand. However, classical learning theory considers IID data, that is independent identically distributed data, and gives optimal algorithms to learn in this setting. In this work, we ask the question, is learning with temporally correlated data harder than IID data? And if so, by how much? We also ask the question, how do we design optimal and computationally efficient algorithms in this setting? Okay. We just consider the setting of least squares linear regression, but however, in our case, the data X comes from a mixing Markov chain. Markovian data is a popular model for dependencies in data, especially in reinforcement learning. We observe X transpose W star plus noise, and we want to recover W star. The noise can be dependent on X or independent of X, depending on the setting we are considering. The kind of algorithms we consider are stochastic gradient descent and other gradient-based algorithms, which are computationally efficient and also achieve optimal performance in the IID setting. If we consider the squared loss, that is for the out of population loss when X is drawn from the stationary distribution of the Markov chain. The least squares regression problem admits a bias variance decomposition for the excess loss, where bias is because our starting point was far away from W star, and variance is because we observe noisy labels. Okay. We first present information theoretic minimax lower bounds for this problem, which hold for any algorithm. Suppose we have t number of samples and the mixing time is tau mix for the Markov chain. We can show that the excess loss is at least e to the minus t over tau mix, which is the lower bound on bias, plus c tau mix over t, which is the lower bound on variance. We do not make any assumptions on the noise independence here. A naive algorithm achieves this rate, that is STD with data drop, where we consider exactly one in every tau mix number of samples and drop the rest so as to make the data look almost IID and apply the IID analysis. We can also show that surprisingly STD with constant step size and averaging may not even converge to the optimal W star even as t tends to infinity. We also derive information theoretic lower bounds for the independent noise case. Here, the model is well specified that the noise is independent of X. So therefore, here the excess loss can be shown to be at least e to the minus t over tau mix. The bias stays the same, but we get a lot of gain in the variance term, that is c over t. Without the extra factor of tau mix. This achieves the same rates as linear regression with IID data. The optimal algorithm in this case is parallel STD, which runs O of tau mix, STD data drop chains in parallel, and then averages it out so that we are not wasting any samples in our algorithm. We again show that STD with constant subsize is not optimal in this setting.
Hi everyone, I'll be presenting SERL, Sample Efficient Ensemble Reinforcement Learning. This is a joint work between IIT Madras, Robot Bot Center for Data Science and Artificial Intelligence, Parallel Computing Labs at Intel, and Facebook. The fundamental goal with SERL is to learn an ensemble of policies in a sample efficient manner. SERL consists of two parts. The first is a learning policies framework, and the second is a policy selection framework. The learning policies framework is inspired by some of the recent developments in deep learning, which can be summarized as follows. Firstly, using a learning rate annealing schedule tends to generalize better than using a small constant learning rate schedule during the training phase. Secondly, starting training with a high initial learning rate influences the local minima to which the model will converge. And finally, the performance of a model depends on the local minima it converges to. Using these ideas, we learn a diverse set of policies by leveraging the performance at different local minima, as you can see on the figure on the bottom left. And we do that with the help of cyclic learning rate schedule, as you can see on the bottom right. As the policy converges to different local minimas, we save the policy parameters, which are then passed on to the policy selection framework. The policy selection framework is the second part of SERL. After generating policies using the learning policies framework, we aim to filter and select a subset of these policies. The reason for doing so is to prevent bias from suboptimal policies that might have been generated during the learning policies framework. We perform this filtering using an optimization framework that tries to balance between policy performance and the diversity between the different policies. As you can see from the figures below, when trying to select a subset of 3 policies from a total of 5, there are 10 possible combinations, and there is at least one unique set that yields maximum performance. The goal is to estimate the subset. Finally, coming to the results and conclusion, we test our framework on 2 major environment suits, the Atari game suite and the Muzoko simulator. We test SERL using a variety of standard deep reinforcement learning algorithms and are able to conclude that SERL is robust, scalable, and works across any deep reinforcement learning algorithms. The sample efficiency in SERL comes from generating multiple policies from a single training run in the learning policies framework and from reusing trajectories during training to find a subset of policies in the policy selection framework. As you can see in the table below, SERL achieves state-of-the-art performance in 9 out of 15 games against state-of-the-art deep reinforcement learning algorithms. For more details, please refer to the paper that has been accepted at AMAS 2021. Thank you for listening.
Hello to all. I'll be presenting our work More the Merrier towards multi-emotion and intensity controllable response generation. And this has been presented in this year AAAI. Now our work is related to the broad areas of developing a conversational AI system that will be empathetic in nature. And this is one of the very exciting characteristics of today's conversational systems. Now, if you look into this particular example, if the listener in response to whatever speaker has said, if the listener says that why would anyone promote you, then the speaker will not feel good and this conversation will not last for a longer time. However, on the other hand, if the listener says congrats, that is great, then the speaker will feel proud of it and this particular conversation will last for a longer duration. Now, in our particular work, we have defined a very new task to generate the responses that will handle multiple emotion and the intensity of the emotions. There has been no data for this. We have created our own data. And then we have proposed two interesting memory-based mechanisms to handle these two phenomena, that is handling multiple emotion and the underlying intensity of the emotions. Now let us see why this multiple emotion generation is really a relevant problem. This particular attendance shows that it has two different emotion categories, and if one of them is left unattended, then the overall meaning will not be complete. At the same time, the emotions can also be expressed with a different level of intensity. So capturing these emotion along with the intensity plays an important role. Now, our architecture, we have an utterance encoder, we have a context encoder to encode the dialogue history. Every state of the decoder depends on this dialogue history, that emotion and the intensity embedding. Also a control signal that is coming from the implicit memory that controls the amount of emotional content left to be generated. We also have an explicit memory that actually balances between the generic and the emotional contents in the final response. We have collected data from 8 famous TV shows, and every utterance was labeled with the emotion and the intensity values. We have performed extensive evaluation, both in terms of the human evaluation metrics and the automated evaluation metrics. And the output that we observe shows that our model is able to conform with the multiple emotions and their intensity values. This particular slide shows how the generated response can vary with respect to the underlying emotion and their intensity values. With this, thank you for your time, and I request all of you to look into our paper to know more about this particular line of research. Thank you once again.
Hi, I'm Preeti, and I'll be presenting our work titled Select Substitute Search, a new benchmark for knowledge augmented VQA, which is to appear as a resource track paper at SIGA 2021. What is visual question answering? You're given an image and an accompanying question, and the image has sufficient information to arrive at the answer. Now, a more challenging variant is where outside knowledge needs to be combined with the image information to answer the question. Now, the OKVQA task was introduced in 2019, and in this data set, we observed many of the questions could not be accurately answered even with outside knowledge. So some questions required OCR, others were speculative in nature, and some questions are vague in their description, and hence the answers are unclear. Current OKVQA systems treat the problem as a classification problem over the K most frequent answers in the training set, and due to large train test overlaps, frequency-based predictions are often rewarded. Also, the reasoning process of existing systems is uninterpretable. In order to address these limitations, we present a new challenge for OKVQA, which is rooted on queries that require a very specific structure of reasoning. The goal is to correctly substitute these creatures in this example with the correct entity people in order to get a reformulated query, which in turn is used to generate answers from a knowledge graph or a corpus. This is our select substitute search or S3 paradigm. We also construct a new dataset that we call S3 VQA that is built from the ground up to be fact-based and abide by S3's main principles. This has also been manually checked for any errors. We start with raw images containing entity or object annotations with parent labels, use the entity to find an appropriate Wikipedia page, extract text snippets, which are then passed to a T5-based question generation system to generate questions containing the entity. And finally, using a set of manually defined templates, the entity label in the questions are replaced with the parent label to obtain questions with the intended structure. We also propose a neural architecture for S3, where a BERT-based span selector first identifies a span, the question that needs to be replaced with some information from the image. Given a predicted span, we want to determine which object from the image would be its best substitute. For this, we use a BERT-based matching module, which is detailed in our paper, in order to identify the object which is the best substitute for the span. We then pass the reformulated query through Google to get a top 10 list of most relevant snippets. These are further passed as input to an MRC module that naturally supports an open domain setting and allows us to bypass the classification setting, which is far more restrictive. This table shows module-specific evaluations for both our data sets in the open domain setting. We also show the standard classification results where we see that our select substitute for reformulation strategy is very beneficial, and the MRC module is instrumental in further improving performance on this task. Now, this is an open challenge which is available at the following URL. Despite consisting of queries which require a fairly basic form of reasoning, this task shows that there is a lot of room for improvement. So we hope this sparks your interest, and thanks very much for listening.
Thanks for your interest in our work on adversarial dualic bandits. I'm Adirupa Shaha. I'm a postdoctoral researcher at Microsoft Research New York City. And this is a joint work with Tomar Koren and Ishai Mansoor. Let's briefly overview what the problem is. So in dueling bandits, generally there are K arms, and it is assumed that out of this K arms, unlike multi-arm bandit, at every iteration, the learner has the provision to only pick 2 arms at every round, upon which it gets to see the noisy preference information of which arm is preferred over the other. The game goes on in rounds in sequentially 40 rounds, and the goal of the learner is to basically do a regret minimization or best arm identification, provided there is some good arm in the hindsight. Now, the problem lies in the fact that over the years, though various studies have addressed this dueling bandit problem, most of them has assumed that the underlying preferences are generated from a preference matrix which is fixed across time and does not change. So, which is unrealistic because in general, the real world systems are always evolving. So the novelty of this work lies in we assume adversarial preferences where this underlying preference matrix P, from where the 0-1 comparison feedbacks are generated, can change every round whereas the learner do not have any idea of what this P is or the sequence of PTs are. And the problem is particularly challenging because from a 0-1-1 1 beat feedback, it is difficult to understand, estimate anything about the property of this matrix PT, which can be used, which is essentially for any learner to learn learn anything about the adversarial dueling minded problem. And also, the challenge lies in what is the notion of a good item in the hindsight against which our regret or the learner's performance should be measured. For that, we come up with a regret objective, which actually defines the regret with respect to the Boda winner in the hindsight. So, the cumulative Boda winner in the hindsight, as the definition of the Boda score is given here, which is basically the probability of any item I beating a randomly picked adversary. And given that problem objective, let's summarize our results quickly. So firstly, we show that there is a fundamental performance limit of this problem that no matter what algorithm you come up with, there is always exist a hard enough problem instance where any learning algorithm has to go through a regret of at least t to the 2/3 in the problem independent setting or k by delta square in the gap dependent setting. Following which shows the hardness of our problem, following which we also designed an upper bound algorithm which has the matching regret guarantee as obtained in the lower bound, justifying the tightness of our analysis and probably optimality of our designed algorithm. So I just do not have the time to go through the technicalities, but the lower bound problem construction or the analysis pivots on the fact that because there are we only see the comparison feedbacks, if there is a set of good arms and bad arms and they are distinguishable among each other, unless we play the bad arms many number of times, apparently 1 by gap square time, it's impossible to figure out which is the Boda winner for any learner. And in the process, the regret you incur is k by delta square or t to the 2/3 regret. Following this, we also have an upper bound algorithm, which is basically an EXP3 based algorithm. And the novelty lies in coming up with how we estimate Boda score of every item at every round from this 1 beat 0-1 preference feedback, but I don't have the time to go through any of these details. We also have some experiments results. I'll skip it for the time being, and we have many future work in mind, extending it to feedback graph, partial monitoring, but I'll skip all the details for the time being because we're out of time.
Hi, I'm Sahil. In this video, I'll be presenting our work on characterizing GAN convergence through proximal duality gap. This has been accepted to ICML 2021 and is a joint work with Aruf Ayman and Dr. Narayanan CK. Generative adversarial networks or GANs aim to learn data distributions to an adversarial game between two players, a generator that maps a latent noise space to the data space and a discriminator that tries to effectively distinguish between the fake data samples generated by the generator and the real data sample. This adversarial game can be formulated as a min-max optimization problem, and as the game proceeds to an equilibrium, the generator learns the real data distribution. A challenge in training GANs is that the min-max optimization alters the loss surface of each player at every iteration. This results in highly non-intuitive loss curves for both the generator and discriminator over time that is non-informative of whether the GAN is converging or diverging. Thus, in this work, we propose a measure that can be used for quantifying and understanding GAN convergence. Since GANs constitute an adversarial game, the notion of convergence is that of an equilibrium. The classical notion of GAN convergence is that of a Nash equilibrium. It constitutes a maxima of the GAN objective function V with respect to the discriminator and a minima with respect to the generator. However, a Nash equilibria is not guaranteed to exist for GANs, and a more generic notion of GAN convergence is that of a proximal equilibrium. It constitutes a maxima of the GAN objective function V with respect to the discriminator and a minima of a proximal objective V lambda defined over V with respect to the generator. Proximal equilibrium is guaranteed to exist, and it covers a spectrum of equilibria for varying values of lambda. We propose to quantify GAN convergence as that of the GAN game attaining a proximal equilibrium. To do so, we introduce the notion of proximal duality gap. For a given GAN configuration, we define the proximal duality gap dg lambda as the difference between the maximum value of the objective function V with respect to the discriminator and the minimum value of the proximal objective V lambda with respect to the generator. Intuitively, dg lambda measures the ability of the players to deviate from a given configuration with respect to the proximal objective. When the GAN game converges to a proximal equilibrium, none of the players have the incentive to further deviate from it with respect to the proximal objective. Thus, dg lambda at a proximal equilibrium would be 0, and this helps quantify GAN convergence. dg lambda also enjoys some nice properties. Specifically, we can show that the proximal duality gap is lower bounded closely by the divergence between the real and generated data distributions. Thus, the proximal duality gap tending to 0 not only implies that the GAN has reached an equilibrium, but also that the generated data distribution is close to the real data distribution. Proximal duality gap also enables us to derive insights into GAN optimality. Specifically, we can show that the generator in both an unbounded or a bounded setting attains the minimum divergence with the real data distribution at a proximal equilibrium. We can also show that GANs can capture the real data distribution at a game configuration if and only if it corresponds to a Stackelberg equilibrium. Please visit our paper using the given link to learn more about our work. Thank you.
Table structure recognition using top-down and bottom-up queues was published in ECCV 2020. Given the table image, the aim is to encode it according to a predefined XML, which includes coordinates, row-column spans, and content for every table cell. Table digitization sees applications from users to enterprises, as it can cause a reduction of cost and turnaround time by up to 6 times. Its solution would allow for easy table visualizations, quick editing, information retrieval, and knowledge discovery. As it is not a problem that can be formulated precisely, it is not as trivial for machines to solve as it is for humans. The end-to-end framework first requires locating tables within documents and then analyzing them for structure and content. While the former is more or less a solved problem, it is the latter which remains unsolved and hence the focus of this work. Some challenges include large inter- and intra-table variances, different indentation of text within the same table, multi-row and multi-column spanning cells, empty cells, and multi-line cells. Researchers have approached the problem in a myriad of ways, which has resulted in inconsistencies across annotation styles and evaluations, making them difficult to standardize and compare against one another. Our work provides a novel solution for table reconstruction and attempts to standardize annotations and evaluations. We devised the problem as a combination of 2 steps, top-down and bottom-up. While we solve for cell detection using our enhanced version of MASCII, our CNN, we formulate our structure recognition network based on the DGCNN architecture proposed by Qasim et al. TabStructNet puts these two together and allows for end-to-end training for cell detection and structure recognition, which allows for better capture of long-range row and column dependencies. We introduce alignment laws to capture the inherent structural constraints of the table. This significantly aids cell detection and in turn structure recognition. We also provide a protocol for standardizing existing datasets, which account for human cognition-inspired constraints on tables and also annotates empty cells. Finally, we compare our solution against state-of-the-art methods across most standard datasets for table structure recognition and obtain best-in-class results. Setup A uses table image only, and Setup B additionally includes content or word locations extracted from PDF or OCR tools as inputs. Here is a demonstration on a sample image. Original site TSR annotation is on the left, while the pre-processed one is shown on the right. Here is the output from our cell detection model, both original and smoothened out. And here is a visual demonstration of the structure recognition, showing rows on the left and columns on the right. Finally, we represent a table image in a digitized format after locating all cells along with their structure and content. Thank you.